So now is cross-validation for the regression task. So the previous one was classification on iris dataset. So here we have a dataset on cars. It's called the auto dataset. I'm loading it. It looks like this. You can see that we have miles per gallon as one variable. This is the response actually. We have number of cylinders of the car. We have horsepower and so on. So miles per gallon is a measure of how efficient the car is, how many miles it goes per gallon of fuel. And horsepower, it's how powerful it is. So generally, cars with higher horsepower have lower mile per gallon, right? So we want to model MPG based on horsepower. And here the data looks like this. The data looks like this. We have essentially miles per gallon on the y-axis and horsepower on the x-axis. So the scatter, you see the data points. We can fit a linear regression on this data. That would be the yellow line. We can fit a degree 2 polynomial or a quadratic model. That would be the blue line. Or we can use a degree 5 polynomial. That would be the green one. So in terms of fitness, which one do you think is a better fit? Degree 2, yeah. So with degree 2, you can see that it's kind of capturing the main patterns in the data. For example, the fact that there's a decrease, but in the end, it kind of slows down. And after some horsepower, miles per gallon doesn't decrease as much, right? The yellow one is kind of underfit because it just says that there's indirect relationship. That's it, right? And the green one, it's kind of fitting to the data more flexibly, but it's kind of going out of its way at the two extremes. For example, here in the end, it kind of goes crazy. It says pretty much, at least to me, that when you increase horsepower at some point, your car actually becomes more efficient. It's doing that because it's kind of trying to fit to these data points here. And as you can see, we don't have many cars, at least in this data set, with horsepower larger than this. And because of that, fitting to these few data points is very risky. It's kind of capturing a lot of noise by doing this. And also at the other extreme, it's kind of off, as you can see. So just, visually, we have a sense of degree 2 being more suitable. But let's see what validation and cross-validation tells us about this. So I'm loading the data. Here, I'm shuffling the data so that I can do a three-way split. So I'm shuffling the data. Now you can see that the first data point is now a different car, right? I just reset the index. Now I can say the last 25% of the data, I use it as holdout data. I call it auto holdout, and this shouldn't be used for training the model or deciding on anything related to the design of the model. I keep the other 75% as training plus validation or accessible data, and I call it auto. So auto refers to the accessible part. Now for deciding on training versus validation. So this is the validation set approach from week 1. The idea is very simple. From the accessible data, we use some of them for training and the rest for validation. So here, I'm taking random numbers in the range of 2/3 of the size of the data, right? And those are the indices that I'm going to use for training. So then I create a binary indicator for these indices to see whether each index should be used for training or validation. So this is actually the R way of doing this. This is because the authors of the textbook are statisticians and the textbook is based on R. That's why this example is kind of more about R than Python. While everything we do in this course is Python, it's not that bad to also have this exposure to R syntax within Python. So here you can see that, for example, the first data point from the accessible data is true. This means that it is selected for training. This one is false, which means that this is used for validation, right? There shouldn't be any overlap. So now I'm fitting a model. So again, this part looks a bit like R. This is because we're using stats model, which is a library in Python that is based on R. So you can see that for fitting ordinary least squares, we need to use this formula, which is just like R. So we fit a regression model of MPG based on horsepower, and our data is auto based on the indices that are for training. We call that select, right? So we fit this, the predictions. These are the predictions we get from that model. The square error is the difference between the true values of response minus the predictions. We square them so that positives and negatives don't cancel out with each other, and we take the mean, and that would be mean squared error. So means, and then we measure the mean squared error on the validation data, on the data, which is the complement of select, right? So here the MSE validation for the yellow model is 22.58. So this is some measure of performance, right? Then we try a model, a different model. We call it LM2, linear model 2. This model is MPG based on horsepower as well as horsepower squared. So again, I evaluated on the validation set, and the performance is this. Now my question for you is, between this and this, which one is better? The smaller one is better because this is MSE, and here we're comparing the yellow line and the blue line, and you can see that the blue line just has better predictions. It's kind of capturing more of the signal. Just visually we can see it. So then if we go crazy with this idea and include all the way to horsepower to the power of 5, that would be a degree 5 polynomial, which is very flexible. So it's going to fit to the data flexibly and capture a lot, which means capture a lot of signal and possibly some noise. So you can see that actually the MSE increases, right? So between these three possibilities, we go with this model, which has the lowest MSE. Yeah. Yeah. There was also a standard deviation, but I actually removed it, and I was going to actually remove it from your version, from the link that you have access to. So the thing is, that standard deviation doesn't really make sense here because these data points are for different residuals of different points in the data. So that standard deviation is not really relevant. Yeah. Yeah, that's also possible because the how we split the data is probably not the same between your computer and Google Colab the system that is running this, right? So if we use same random seed and both of us run it on Google Colab, we should get the same result. Well, then I guess the systems that we get from Google Colab are also different. Yeah. Yeah. Yeah, we look at the mean squared error. Yeah. Here, yeah. I should have called this MSE. Yeah, I kind of got confused myself while I was preparing this. Yeah. So these are MSE, right? We go with the model that has the lowest MSE. At least on my computer, it's this model. And yeah, but the thing is, actually, if we split the data differently, same proportions, but just based on a different random seed number, the results would be different. That's why validation set is not a reliable method anyways. So don't worry too much about this because we have cross-validation, which is the better method. So with cross-validation, here I have the data. I set them to X and Y. And now I'm going with tenfolds. So it's a tenfold cross-validation. And this is another way of implementing cross-validation. So here we're measuring mean squared error, but I'm using cross-val score, which only has a scoring of negative mean squared error. Then I need to put a negative in here. So then you can see that I'm checking polynomial of degree 1, 2, and 5. So that's the same three models that we had. And with cross-validation, not only we get the mean, but we get the standard deviations. This is the part that I was a bit confused. So you can see that mean is 24 for degree 1, it's 19.2 for degree 2, and it's 19.3 for degree 5. And actually these measurements are much more reliable than these measurements. Because if we repeat this cross-validation with different random seed number, we get very similar numbers. But for validation set, we get different values. So, and there are also these standard deviations. So these standard deviations are like those mysterious error bars that I had in my notes. So let me